Welcome back to the friendly blue pen land, right? We had some atomic models, right? And the Rutherford model is the planetary orbit model where the centrifugal force needed is provided by the Coulombic force, and this electron is left being here and going back and forth, and so the problem with that is that, of course, if you make an electron go back and forth like that, it's going to radiate energy. And how does it do that, right? And then the second problem with this was that this atom had no way to account for the spectral lines that they were seeing. And we'll look at these in class. We'll actually look at these things in person in class because they're very cool. Okay, but this is what you can see if you use a diffraction grating and point it right at these are like neon tubes, right? Okay, you'll actually see these little bright lines off to the side, and this is how, and it's like fingerprints, right? Every element's got its own particular spectral lines that it makes. So that neon red is actually a mixture of red and yellow and green, and there's even ones that we can't see that are infrared and ultraviolet. And we'll demonstrate this when you come to class. I've actually got a setup for this, right? And the wavelengths seem to follow a pattern like this. They'd approach things like this. Here are things that, of course, you can see. This is infrared, right? Because visible light is like somewhere in here, right? And then these guys are actually ultraviolet. They're very short wavelength, right? But they map these out, and some high school teacher named Rydberg, a German high school teacher, okay, actually made a formula for this, right? Here's this this constant. That's the Rydberg constant, right? And he came up with a formula here. Now, if you're looking at this and you've already know the answer, of course. These look a whole lot like numbers, like integers, right? And these are probably the Bohr orbits, right? Okay, but this is, of course, this formula was there before there were Bohr orbits, right? Okay, but this is very cool, right? All of this, of course, irked the physicists who did not have any physical basis for this. Okay, now. Bohr, the basic idea is this, right? Is that and Bohr actually derives this equation. He actually came up with an equation to describe this, and he starts off the derivations in the book. I used to do it, it'd take like an hour, and kids would fall asleep and they drool all over their desks, right? But if you read it in the book, they actually go through it, and they start off by setting up an orbital, like Q over R squared. Is mv squared over r, just like we did with orbit problems, right? They set the thing up like that, and then Bohr basically knows that he's got to quantize something, and he makes this ad hoc sort of quantum thing to make it have orbits. And the question is, why would he do that? Well, here's the answer. The answer is in the back of the book. It's right there. Okay. Now, the important thing that you need to understand about this is that in the Bohr atom, these transitions, okay? These transitions are like for example, this thing here, we're talking about going from an upper orbit down to a lower orbit. The electron is here, and it makes a quantum jump to here. It doesn't move from here to here, okay? It is here, and it's there later. It is never observed in between. When it makes that quantum transition, right, this is a lower energy level, right? Okay, so when it does that, it shoots off a photon. That was the basis of the Bohr atom. That's eventually how he predicted these things, is that these little spectral lines are all transitions from maybe this orbit to this orbit, or this orbit to this orbit. That would be more energy, right? This orbit to this orbit would be even the most energy, right? That might be like an ultraviolet photon, right? So this is the basic idea. This is really pretty simple. And that's what Bohr did, was he came up with the actual formula, based it on things like the electron charge, and Coulomb's law, and energy, and he predicted these things from that. He came up with this formula from physical predictions. Okay, notice that the Balmer series, right? These guys here are visible light. These transitions are there's so little energy that this is infrared, right? We can't even see it. It's so low energy. This is visible. And then these guys, look out, these guys will give you a sunburn. This is ultraviolet. They got so much energy, right, that these transitions are invisible because they're ultraviolet. Okay, so, here's an example problem, right? What's the wavelength of the first Lyman line? Okay, well, the first Lyman line goes from here to here, right? This is the second one, the third one, the fourth one, the fifth one, the sixth one, etc., right? Okay, and so it's going from negative 3.4, right, down to negative 13.6, right? That is a total energy release of, I need my calculator to do that, 10.2, right? Okay, so this is the only physics that's here, right? Is that you have to see that the difference in energy level from here to here, okay, is 10.2 electron volts. Do we see that? Okay, because everything else is really pretty simple. I'm going to go 10.2 electron volts, right? I'm going to multiply by 1.602 E minus. I'm just using my photon stuff, right? This is joules per electron volt, right? Okay, so 10.2 times 1.602 E minus 19 is 1.634 04 E minus 18th joules, right? And then let's see, energy is hc over lambda. So lambda is hc over E, right? So it's 6.626 E minus 34 joule seconds times 3.00 E8 meters per second, right? Divided by 1.63404 E minus 18th, and that's joules, right? And of course, this all works out to meters. We've done this 100 times before. Okay, so 6.626 E minus 34 times 3E8 divided by the answer I just got. And I get 1.21649 E minus 7 meters, right? So if I move the decimal point over there, I get 121.64 times 10 to the minus 9th meters, which is about 122 nanometers, right? Ta-da. So there's an example of one, right? Okay. Ta-da. Okay. Now, the limitations of his model are as follows, right? It worked really well for hydrogen, okay? As soon as you get another electron running around, Bohr's model has problems because the electron, if you've got a nucleus here, right, and you've got another electron here, negative charge, if you've got an electron in an outer orbit, this thing actually shields the charge of this one, right? It acts as a repelling thing, so the electrons interact. And so that was a real problem. Helium didn't really even work for. Okay, it didn't explain. It turns out that some of the lines are what looks like one line actually is a couple lines, right? And this is, of course, there's spin up, spin down, and all these other quantum numbers, right? It didn't explain why some lines were brighter than other lines, right? There was a probability piece there that certain transitions were more probable than others, right? Molecular bonds, well, no, we weren't quite there. In fact, we're not there yet. Right, and the idea here, people say, well, the Bohr model is wrong. Well, it's not wrong. It's just not the whole thing, right? But generally, it was a good thing, right? Okay. So there's Bohr. Here's Bohr with a mustache. That's him as a young man, about the time that he published this. Okay. Hey.